This is the prep video for finding derivatives of logs and exponentials. So before we get started, we actually need to remind ourselves what those are, what those graphs look like. So an exponential, remember that means the variable is in the exponent. So for example, y equals 2 to the x. This would be a great opportunity in class. I'll probably in class use Desmos to show you that. So here, the thing to remember is if I put in x equals 0, right, we always look for y-intercepts first. I'll get 2 to the 0, that's 1. So this graph looks like that. A log function is the inverse of that. Most commonly we will use, let me back up. That's ln x. More generally, we can write log base, whatever, base b of x. Ln x is just simply using base e, which we will use. Remember, e is just 2.7 something. So another example of this, e to the x. Okay, so this is a log function. It is an inverse function, so we can think of it as being reflected about the y equals x line. So this is going to go like this. It has a vertical asymptote. This one has a horizontal asymptote. Okay, we also need to remember some laws of logs. So let's come over here. Hopefully I have space. So laws of logs. So which one do I want to start with? So if we have log AB, multiplication on the inside turns into addition on the outside. Log of A divided by B, division on the inside turns into subtraction on the outside. And then the one that we'll actually use the most is log, make sure I match the notes, log A to the P, I'm not sure why I picked P, would be P log of A. So this is the one, again, that we'll use the most, where we'll take if it's a variable to an exponent, or any value to an exponent, the exponent can come down in front. And now I have just a basic log. The thing that I'm going to suggest that you do is that if you have 2 times log x, those two are multiplied together, I recommend that you write that as 2 log x and not log x times 2, because it's not clear whether that 2 is inside the log or not. And then one last reminder is that remember when you're computing using exponentials, exponents and logs on your calculator, make sure to end your parentheses to make sure that you don't include extra things inside the log or the exponential that you didn't need. Okay, so that's kind of some review. We're also doing derivatives, so one more last little bit here somewhere. The last little bit, remember about derivatives, that multiplication by a constant, addition and subtraction carry through. So we can, whatever we have on in the function itself, we can just mirror that pattern, plugging in the derivatives as we go. So multiplication by a constant, addition of functions, and subtraction. All of those carry through. When you're doing the derivatives. Okay, all right, so we have everything, all of our kind of our basics there. So let's do some examples. First, let's start with rewriting some things. Then I'm going to introduce derivatives, and then we'll do some practice derivatives. So the first thing is let's do some practice rewriting. So we want to rewrite the following things in basic form. That means getting all the way down to just log of x. So the first thing I see here is I've got 2 things multiplied. A 2 times an x cubed, so multiplication on the inside turns into addition on the outside. And then I have this exponent, which can come down in front. So log 2 ln 2 plus 3 ln x. Okay, here's another one. Ln 2x plus 3 over 4x plus 5. I see division on the inside, so it turns into subtraction on the outside. Can I do anything further? No. This is addition on the inside isn't anything. And I can't split that apart to get to that multiplication. So this is kind of as simple as this gets, which is just, that's our last example, which is just a reminder of that. There's nothing, this is as simple as it can be, using these laws of logs. Okay, so that's just some practice working with logs. All right, so now let's define some derivatives. Let's start with the exponential, and if you look at this, this is a function that starts with a low value and goes up to a high value. Let's look at the slope. The slope starts low, and then the slope goes to a high value. So what's interesting is that the derivative of e to the x is itself, it's e to the x, and that makes sense from the graph. The graph gradually rises and then it starts to really accelerate, and the slope does the exact same thing. So let's write that over here. For y equals e to the x, its derivative is e to the x. Okay, for y equals ln x, its derivative is 1 over x. Does that make sense? Well, when x is really small, the slope is very steep, and then it starts to get lower as x gets higher. So that's an inverse relationship, so yeah, that makes sense. Okay, so let's do some examples. Okay, and let's find y prime. Okay, so let's take it piece by piece. So here's 4 times e to the x. Multiplication by a constant carries through. Derivative of e to the x is e to the x. Plus 4 times, what's e to the 2.7? That's all actually just a number. What's the derivative of any constant? 0. Okay, so don't be fooled by that. The 2.7 doesn't come down or anything because this is just a number. All right, here's another example. So that's 1. Ln x minus ln x to the 7th. So we want to find dy dx. So looking through, multiplication by a constant, subtraction no problem. This is not, look here, all I have is ln x. That's all I know the derivative for. So I have to rewrite this before I can move on. So we need to write 5 ln x. We have laws of logs. We know that this exponent can come down in front. So minus 7 ln x. And then we could just go ahead and take the derivatives. Or, and sometimes this happens with logs, I have 5 ln x's minus 7 more ln x's. I can actually combine like terms. They are all ln x, so 5 minus 7, negative 2 ln x. So now I can take the derivative of that. Negative 2 carries through. Derivative of ln x is 1 over x. And really, this is not a good way to leave this. You should really clean this up because it's easy to just simply write this as minus 2 over x. And I prefer myself the minus sign in the negative sign in the front rather than in the numerator or the denominator, but this negative sign could go any one of those 3 places. Out front, numerator, or denominator, but not multiple places. So just to show you that this, in fact, was not magic, let's go ahead and do the derivative based on the first line. So that would be 5 times 1 over x minus, remember, because multiplication by a constant and addition subtraction carry through, 7 times 1 over x. So again, we're collecting like terms, negative 2 times 1 over x and so on. So just remember with logs, sometimes you can combine things before you take the derivative and just save yourself some time. Okay, one last one. 2 last ones, I guess. Not everything is y and f of x. Sometimes we have other functions. And we want to find g prime. So that implies that it's with respect to x. So let's look at these. I wanted to draw your attention to the fact that exponentials and powers look the same, but they're really very different. It all depends where the variable is. So here the variable's in the exponent. We haven't gotten here yet. I'm sorry, I skipped ahead. Let me come back. Sorry. All right. Len, so this is the one I meant to do. All right, so this is f of x, and we want to find f prime. Okay, so again, we only have len x. This has got a lot more stuff in the middle, so we need to break it apart first. So I see division on the inside, so that's subtraction on the outside. So that's better. But again, I only have len x, so I have to deal with the exponent there. I'm going to bring it down in front. Okay, so now we're ready to do the derivative. 3 times the derivative of len x minus len 5. That's a constant. You can find that on your calculator. So the derivative of the constant is 0. So altogether, 3 over x. Okay, so that's working with base e. So remember, e is just a number. It's a number about 2.7, a little bit more. And len is really just log base e of x. So now we need to introduce, what happens if we don't have base e? Okay, so we have another set of derivatives which are very similar but not quite the same. So, sorry to write these down low, but I will. If y is equal to any other base besides e, anything else, its derivative, it follows the same pattern. It's still b to the x. But now it's got what I like to think of as kind of a correction factor, just to fix up the fact that it isn't base e. And so what you need to multiply by is len b. Likewise, if I have y equals log base b of x, it's going to be the same 1 over x, same pattern, so the derivative is 1 over x. And now its correction factor, it has the same len b correction factor, but it's in the denominator. Okay, so now we're ready to do some more examples, the one I had just got started on. Okay, so now let's look at this one. E to the x people recognize very quickly as an exponential, but sometimes these throw people because one's an exponential and one's a power. The exponential has the variable in the exponent, and then the power has it as the base. So if we're going to find the derivative of this, 2 to the x, that falls in this category. It's an exponential, but the base is not e. So we know that we will have that same b is 2, so we'll have 2 to the x, but then we have that extra correction factor. So this would be 2 to the x len b plus, and this is just review, that's just straight power rule. So just take them separately. Power rule, exponent comes down in front, exponent goes down by 1. So just again, remember the difference between these two. And then here is our last one. H of x equals log base 5 of x plus log base 5 of 3x. And we want to find dh dx. Okay, so let's look along. Log base 5 of x, that's a basic, but it's not a base e. So that means we're down here. We'll still have the 1 over x, but then we have the correction factor. And then coming along, this one is also not base e, and it's also not a basic. So we actually need to do a little bit of rewriting first, so let's do that. So this one is fine. This one, multiplication on the inside, addition on the outside. So log base 5 of 3 plus log base 5 of x. And again, it's always worth, particularly when you're rewriting logs, to make sure that you look for like terms. So here I have a log base 5 of x and another one, so 2 of them. So 2 log base 5 of x plus log base 5 of 3. So I recognize that these were logs, but not their most basic. Rewrite, combine. Now we're ready for the derivative. Okay, so addition and subtraction and multiplication by a constant carry through. So we'll start with 2 times the derivative of log base 5 of x. So it's that same 1 over x, but because it's not base e, we have a correction factor. What about this one? Log base 5 of 3. That's a number. You can find that on your calculator. So the derivative of a constant is 0. And to clean it up, I would probably write it as 2 over x ln 5. Again, I wouldn't put the 5 on the other side because then it might look like 5x was altogether in the ln. So I know I wrote a lot on the board, but this down here is kind of the new take-home part. The derivative of an exponential is an exponential. If it's base e, it's that. If it's any other base, you just multiply by a correction factor. The derivative of ln x is 1 over x. If it's any other base, you divide by the correction factor. So that's it.